After building the logic for the transmitter and receiver and the whole UART core, now we're ready to plug it into one of the I/O slots in our prototyping system. So what we need to do is we need to come up with a register map and a wrapping circuit so that it comply with the MMIO controls that we've seen before. So let's take a look very briefly about what do we need for the register map. So generally speaking, I take a look at my module. My module in here, I basically put a bounding box because as a processor, I don't care how it's implemented. What I care about is how do I interact with it. So what does the processor see? Well, the processor sees some FIFO that it can read from, the FIFO for the receiving part. So it should have some R data, it should have some read UART, and should have RxMT. And I believe these are here. So you will have the read data, for example, which is 8 bits. You have the read UART, which is actually a signal that it can actually write. And you'll see the mode in here. This is read, this is write. And the same goes with the RxMT. Just make sure that that FIFO is empty or not. So it can test it. Like, is there something that I received and it didn't read as a processor? The same thing goes with the write part. So the processor can write into the FIFO, okay, and what it has again, it has basically a write UART, which is actually this particular signal that asserts a write data, like which is 8 bits, and of course it can figure out whether the FIFO is full or not before it actually sends anything, so it's actually a read signal. One more thing that it actually also can interact with the UART core here, which is actually the divisor. So the divisor is actually based on the value of the baud rate. We are computing the divisor and we will compute it using the driver. So that equation that we've seen before when we talked about the divisor and the baud rate generator, we're just going to do it through the driver. So as a hardware part, we're just going to provide it with some sort of a number that tells me how many ticks, or like it will count towards it. So it will control the number of ticks it does. But anyway, as an application developer, you shouldn't be too worried about how to compute this divisor. The driver developer should. The other signals that you don't see, of course, the clock in here, which is basically runs the whole system, which is obvious. I mean, the processor doesn't need to interact with the clock, but the other two signals are the RX and the TX, and these are actually not connected to the processor. They're connected to the outside world, to a different system. Okay, so we don't need it in our register map. So all we have to do is just take this information and just put it within some sort of a register map. We know that an I/O core can have up to 32 registers. Each one of them is 32 bits. And what we see in here is a suggested register map. This is definitely not the only way we can actually construct a register map, but it's just a way that we can do it. Okay, so what does this register map do? Well, this register map did a look at this mode in here and decided to put all the read together. Okay, so we have a read data, which is 8 bits, so we're going to put them in here. And we have a couple of status signal, which is whether the receiving end is empty or not, and whether the sending end is empty or not. We're going to put them in bit 8 and bit 9. And basically, if the processor wants to read some data, it actually can read it in here. And if it actually wants to read some status signal, it can just read this particular register, and that's about it. The other thing is actually our write signals in here. So this one here is just a divisor. It's that simple. This one here is just a write data. That's simple. This one here is actually a dummy write data, or dummy data write. It's actually not listed in here. And its purpose is the following, is because we have here, what we have is we have a bunch of FIFOs. So we can definitely put some, like, this is actually for the read part in here. So for the read part, the processor can definitely goes and issue a read UART here, so that if the FIFO would actually move to the next data point and just release it. And if this FIFO usually is a first word fall through, and it just falls. But what we're going to do it a little bit differently. We will do it in a way that the processor is not going to issue this read UART in here. It's just going to issue some write data, and it's going to write whatever garbage it is in this particular register. And once it does, we're going to just assert that read UART signal for one clock cycle. And that's how we're going to be basically moving to the next word in the FIFO. So let's take a look at the wrapping circuit. So as we expect, the wrapping circuit has the standard slot interface, so we can actually plug it into the MMIO controller. They're the same exact standard signals. And of course, it has a couple of external signals, which is RX and TX, which we connect to the outside world. A bunch of signals here, so for the internal connections. And what we really have is a UART that is basically instantiated the UART that we constructed. The parameters are set in here. The FIFO is actually connected, the FIFO depth is 8. That means 2 to the power 8, it can actually have up to 256 rows. So it's pretty large. And then we have connected the divisor to some sort of a divisor register. And as it turns out that this divisor register is in here. So we're going to actually define some new register, and we're just going to put it that here. So we defined the new register that is 11-bit, exactly what we do. And we connected it to the input in here. So we're going to save that divisor, that baud rate, because we need it to be saved. So technically, if you think about it, we have a FIFO in here and a FIFO in here. So some of the registers, for example, the read data and the write data, we don't need to specify them as exactly physical registers because our system has FIFOs in it. So all the processor needs to do is just write into the FIFO. So we don't need, in our wrapping circuit, we technically do not need to have a register to store the R data or the write data. Technically, we can directly connect it to the address to the processor right all the way through the MMIO controller. But we're doing it a little bit differently, and it's really interesting. So let's see how it's actually done. So we are connecting the write data, okay, to the write data. So these are actually connected to the MMIO controller. The read data is also connected to the read data. The reason why we're putting these is one is called W data, the other one is WR data. Okay, for some reason this is what we decided to connect it or call it. In here, what we have is the divisor register. This is this particular register is just the only register we're actually implementing in here. If you take a look at that, I don't have a bunch of, except for the odd register in here, I only have the divisor register. And you're going to see that this odd register is not actually really, it's not like something a little bit different. We'll see shortly how we do this. So the divisor register, this one here, how does it do it? When the reset, we put 0 in it. If it's not reset, we're going to see if the signal, which is write divisor, is asserted. We're going to put whatever the processor decided to write. Okay, so the processor is going to write something in here, and we're going to write it, and we're going to store it in this particular register. So let's take a look at the decoding logic. So if you think about it, decoding logic, decoding means that we are writing into the register. Okay, so these are all of the write. So when do we write? When the processor wants to write, when it chip selects my particular module, and now we have these in here, and these actually apply to all of them. So whether you're writing the divisor or writing to the UART or actually doing a read UART. Interesting. What does the read UART does? It's actually this dummy here. We'll see it shortly. So let's see what the WR divisor is. The WR actually goes and tests, am I in offset number 1? Because this is offset number 1. Okay, if that's the case, I'm going to enable that signal, and this signal actually led to the write of that particular value that the processor wanted into this particular divisor register in here. The next one is actually a UART or write to the UART, which is actually the ones in here. Okay. What does it do? Its testing is my offset number 2, which is actually this one here. If the offset is 2, I'll just basically write whatever the processor wants to write into it. So basically, I'm connecting to that right to that processor, and that's it. There's nothing else to it, and this is actually connected somewhere in here. Okay, it's called WR UART, and that's it. And read UART in here is also the same. So what the read UART in here is actually related to the signal. So let's see how this signal is asserted. Instead of letting the processor actually write like specific things to it, what we are asking, instead of basically telling the processor that, hey, we want to read something in here or write it or assert that, what we're doing is we're telling it, okay, go and write something, processor, go and write something in offset number 3. That's what we're doing. If the processor is trying to write something to that offset, I'll just assert that. What is it trying to write? I don't care, because this isn't what I care about. What I care about is that. So why do we do this? The reason is why we do this is because this read FIFO in here. Remember, the first word fall through, that write data is actually available all the time in here, and I can move to the next line or the next value in the FIFO by issuing some sort of a signal in here. So I'll have to figure out when to issue it exactly, and there's some sort of a timing, weird timing things that the processor needs to deal with. So technically, I can just take this and make it into a write and do the decoding into it and whatnot. But I think it's just easier to write this dummy data in this particular register, and that's it. Last is we did the decoding, so we need to do multiplexing. Frankly speaking, you really do not need to do multiplexing, because multiplexing is for reading, and I'm only reading this particular offset, nothing else. So I don't need the address for the multiplexing. All I need to do is just concatenate the data I want the processor to read, and it's actually the R data, the RX empty, the TX empty, and then I'm going to put a bunch of zeros in here. And that's pretty much it. This is how the wrapping circuit is. So we're going to take this particular wrapping circuit or this particular wrapping circuit in here, which actually wrapped that in here. Okay, and we're just going to plug it into the MMIO controller, and our UART is ready to go.